Good morning, dear students. We are going ahead with the last topic in Module 5. It is the Moore modeling of sequential circuits. So here we'll be covering problems based on Moore model of finite state machines. So this is the first problem that we are going to look at. So by seeing the state diagram, you can easily identify that it is a Moore finite state machine and it's not Mealy. Why? Because in each of the state, output is defined. For example, for state A0, zero output is defined. For A1 state, 1 is the output. For B0, 0 is the output. For B1, 1 is the output. And on the transitions or the loops, input is written. So now what is the first step? We have identified that it is a Moore model. And what is the next step? You identify the number of bits required for inputs and outputs. So here you can see that input has 2 bits. Look here, input has 2 bits. And we call it x1 and x2. x1 x2 pair, okay? And what about the output? Each state is associated with an output and output is represented by 1 bit. Let us say we are representing the output bit by Z. Now how many states are there? It is having 4 states and it has been labeled as A0, A1, B0 and B1 in the state diagram. Now what is the next step? The next step is obtaining the state table from the state diagram. So from the state diagram, you're going to obtain the table. So you write the present states first. How many present states are there? A0, A1, B0 and B1. Next, you write next state for each of the input combination and separately the output will be written. Because it is Moore, each of the state will be having an output. You don't write it together with the next state. Because according to the input, the output is not changing. That is why it is written separately. So this can be immediately written. For example, for A0, what is the output associated? It is 0. For A1, it is 1, B0, 0, B1, 1. So output is written now. Now how will you write the next state for each input combination? First write the input combinations 0, 0, 0, 1, 1, 0, 1, 1. Now you first take about the first state A0. When the input combination is 0, 0, it remains in A0. That is what is written here. And when the input combination is 0, 1 or 1, 0, it goes to A1. Look here, for 0, 1 and 1, 0, it goes to A1. Now, if the combination is 1, 1, what happens? It goes to B0. Look here, it goes to B0. So this is how you write the or fill the inside of the next state column or rows, okay? Now you take another state. For example, let us take B1 just to make you more familiarized. Take the state B1, this one, okay? What happens? When the input 0, 0 is applied, what happens? Look here. It goes to A1. That is what is written here. And when input of, look here, outward loop should be taken. Arrow should be outward. That is what is indicated by what is the effect of each of the input on B1. All the outward ones should be taken for each state. Okay. Now when 0, 1 and 1, 0 is applied, when the machine is in state B1, what happens? It goes to B0. That is what is written here. Now when what is the 1, 1? Look here. 1, 1 is self loop. It remains at B1. That is what is written here. So similarly, you can fill the other uh, rows in the table and you can complete it. Okay. Now, after getting the state table, what is the next step? The next step is actually the process called state assignment and forming the transition and output table. Here there is no need for transition and output table because in Moore modeling you are writing already the next state and output is written separately. So actually there's no significance for this one. You can just call it state assignment. In state assignment, what you do? You give values for your states. So you're going to give value of A0 as 0, 0, A1 as 0, 1, B0 as 1, 0 and B1 as 1, 1. So you assign that values. Now, what is the next step? The next step is choosing the type of flip-flops and forming the excitation table. So here, first what you have to write? You have to write the present state, you have to write the inputs, you have to write the next state, you have to write the output, and in addition, you require the flip-flop inputs. So, what did I tell you? How can you write the present state? Since you are having 4 states, it requires 2 bits. So you call it y1, y2, small y1, y2. And next state you are going to call it capital Y1, Y2, right? Now take present state 0, 0. How many inputs are applied? 4 inputs. That is how you have to write. Look, present state when it is 0, 0, you have 4 inputs being applied. Similarly, when the present state is 0, 1, look here, you have 4 inputs again being applied. And also for 1, 0, again 4 inputs are applied. For 1, 1, again 4 inputs are applied. So I think you can now easily write the present state and input in the table. Now, how are you going to write the next state and output? You know that when the present state is 0, 0, whatever the input is, your output is 0. So it's very easy to fill the output table. Look, for present state 0, 0, your output is always 0. Similarly, when your present state is 0, 1, your output is always 1. It means that for Moore, depending on what is your state, it decides the output. For each state, it will be having an output and it is not dependent on the input application. Now, the problem is writing the next state, okay? Look here, you write this in order. First take the case of present state 0, 0. For each of the combination in order it is 0, 0, 0, 1, 0, 1, 1, 0. Look here. 0, 0, 0, 1, 0, 1, 1, 0. Similarly, you can fill the others. Now, the question is how you can form the flip-flop inputs. So, you are having present state 2-bit, next state also 2-bit. Here you are calling it by small y1, small y2. Here you are calling it by capital Y1 and capital Y2. How am I going to find D1 and D2? You have to take small y1 and capital Y1. This forms your Qn plus 1 combination in your excitation table of D flip-flop. And from that you find D1. It is D1. Now take small y2 and capital Y2 and find D2. For example, look here. My y1, small y1 here is 0. Capital Y1 is 1. 0, 1 combination of D flip-flop excitation table. You get 1. So that's why I said you have to be very thorough with the excitation tables of each of the flip-flop. Only then you can write it very soon. Okay? So similarly you can find all the other D1 inputs and D2 inputs. Now The next step is forming the K-map. So usually for what all you will find the K-map. You will find the K-map for EZ. You will find the K-map for flip-flop inputs. Here you have two flip-flops and you have to find the equations for D1 and D2 separately. So by taking what? By taking the present state small y1, y2 and the inputs. Input is also 2-bit x1, x2. These four as the input of the K-map. You find the equations for D1 separately, D2 separately and Z separately. Now look here, what is this? This is actually x1 x2 plus y1 into x1 plus x2, right? And what is this? This one you will get it as x1 complement XOR x2 complement, or it is actually x2. It's actually y here, y, it's y1, sorry, it's actually y1, it's wrong. It's actually y1 XOR x1 complement XOR, no, it is actually y1 XOR x1 XOR x2. That is what is the equation is, okay? y1 XOR x1 XOR x2. And this one is x1 x2, this one x1 x2 plus y1, you can take it as common, into x1 plus x2. So that way you can draw the equation. Look here, take x1 x2, give to an XOR gate, you will get x1 XOR x2, and y1 you are again taking here, you will get x1 XOR x2 XOR y, and that is your D2. Your Z is y2, and what is your y1? x1 x2 you took it here and you got x1 y1, x2 y1, x1 y1, again you form D1. Just implement the equations. So as I told you, please don't forget what is y1 and y2. It is actually like your counter q1, q2. Instead here they represented it by another name, y1, y2. So y1, y2 is actually the state and it is actually the flip-flop output. So please don't forget that. Now let us go to one more problem regarding Moore model. Look here. It is again Moore because why? Output is tied with the state and on the loops you have just the input. So here how many bits for input? 1 bit. Say you call it by X, and output 1 bit. You call it by Z. How many states? 5 states, A, B, C, D, E. 5 states are there and you call it by A, B, C, D, E. Now what is the next step? Obtaining the table form, state table. So you write the present states, you write the next states for each of the input combination, and you write the output separately. So for each of the state your output is 0 except for state E where the output goes to 1. So this two you can write immediately. And what about this one? Take this case, state A. When you are providing input of 0, it remains in state A. Look here. And when your input is 1, it goes to state B. When in state B, if you're providing 0, it goes to state C. Look here. And when you're providing input of 1, it remains in B. Similarly, you can fill the others. Now what is the next step? I told you there is no significance of transition and output table in Moore because you're already directly writing the transition and output table separately in the previous step. And you are just more interested in state assignment. So here you are having 5 variables. So is 2 bits sufficient to represent the 5 states? No. With 2 bit you can represent a maximum of 2 raised to 2 or 4 states. For representing 5 states you require 3 bits. So you can assign the states this way. A is 000, B is 001, C is 010, D is 011 and D is 100. In that way you can assign the states. Now what is the next step? The next step is actually choosing the type of flip-flops in the excitation table. So if nothing is specifically asked, it's always easy to go for D flip-flop. But if specifically some other flip-flops has been asked, you have to go for it. Okay, so in your excitation table, what do you write? You write the present state first, then the input, then next state, input to the flip-flops, and you write the output. So here, I told you the states are represented by 3 bits, so you need to take small y1, y2, y3. Similarly for next state, capital Y1, Y2, Y3. Input is of 1 bit X. Now, output is of 1 bit EZ. Output is of 1 bit, you call it by EZ. And what about the input to flip-flops? Your present state and next state are 3 bits, so you require 3 flip-flops. Now, how will you write this? Look here. First, take the case of state 000. You have 2 combinations. Look, state 000. Okay. Look here, state 000. You have again, what's happening? You have 2, you are writing it 2 times for input 0 as well as 1. Similarly, 001, you're writing 2 times for each of the input combination and so on. Then you write the combination of input. Now, I told you except for the last state, the last 2, 100, 100. For that too, you write the output as 1. For all others, it is 0. Now, how will you write the next state? Look here. First, take this state. Next state is in order. If input is 0 and 1, it is in order, okay? 000, 001. Look here. It is 000, 001. Similarly, you can fill the others. Oh, it is not that. 000. Here it is. Just a second. 000, 001. Next state. And based on this first bit y1, small y1, and here the first bit is capital Y1, you have to find D1. Similarly, based on small y2, capital Y2, D2. And based on small y3 and capital Y3, you have to go for D3. So, this way you can complete the excitation table. And what is the next step? Forming the K-maps. So here how many K-maps you need? You need the K-map for D1, you need the K-map for D2, you need the K-map for D3, and you need the K-map for EZ. Okay. So what are the inputs taken? Your present state, that is Y1, Y2, Y3 and input. Input is 1 bit X. So Y1, Y2, Y3, X. Using all those 4 variables, you are going to form the K-maps for D1 separately, D2 separately, D3 separately and EZ separately. So you obtain the equations and then you implement. I have not drawn the diagram, you can try it yourself. So I hope now if you are given with the state diagram, you know how to identify the state diagram, whether it is corresponding to milli or corresponding to Moore, and how can you write the state tables and do the excitation table and form the equations and draw the circuit. So if you're asked with such problems, you have to do the entire steps until you draw the circuit. So you have to be very thorough with all these. Especially you need to be very thorough with your excitation tables as well. So that's all. So we have come to the end of the 5th module. If you have any queries, please ask me. Thank you.